Welcome everyone! As we kick off our journey into electrical circuits, we're going to start with one of the most elegant and honestly, one of the most common tools you'll ever use. Today, we are taking a deep dive into the voltage divider. Trust me, you are going to see this circuit for the rest of your career.
But before we get buried in schematics and formulas, let's start with a little puzzle. How does a simple, physical knob like this one control the volume of a really complex amplifier? It kind of feels like magic, right? Well, it's not. It's just pure, simple electrical engineering. And the answer, as you probably guessed, is the voltage divider.
So here's our plan for this explainer. We'll start with the basics. What is it? Then we'll figure out the formula that makes it all work. After that, we'll see how to make it adjustable, check out where it's used in the real world, and then wrap things up with a design challenge so you can put what you've learned to the test. Okay, let's get right into it. First things first, what is a voltage divider? We're going to start with the core idea here, which is all rooted in how series circuits behave. At its heart, a voltage divider is really just a chain of resistors connected one after the other, in series. Its main job? To take a bigger input voltage, that's our Vs here, and chop it down to create a smaller proportional output voltage. See V2 across R2? That's our output. Now the key thing to get is that in a series circuit, the voltage that drops across each resistor is directly proportional to its resistance. So if R2 had twice the resistance of R1, the voltage V2 would be double V1. It's really that simple and that powerful. Now for the part that lets us actually calculate and design these things with precision. Let's build out the essential formula. This is one you'll want to have in your back pocket, always. We can figure out the voltage divider formula in just 4 logical steps. We always start with the foundation, Ohm's law, V equals I times R, right? The voltage across any resistor is just the current through it times its resistance. Second, because it's a series circuit, the total current is easy. It's just the source voltage divided by the total resistance. Third, we take that expression for current and we plug it right back into our first equation. And finally, we just move the terms around a bit to get our clean, final formula. And this is it. This is the magic formula. The voltage across any particular resistor, let's call it Vx, is equal to the ratio of that resistor's value, Rx, to the total resistance of the whole chain, Rt, all of that multiplied by the source voltage, Vs. It's basically telling us that the voltage splits up in direct proportion to the resistance. Let's make this real. Imagine we have a 10-volt source, a 100-ohm resistor, and a 56-ohm resistor, all in series. Let's walk through the math. Step 1. Find the total resistance, RT. That's easy. You just add them up. 100 plus 56 gives us 156 ohms. Step 2. Find V1 across that 100-ohm resistor. We take its value, 100, divide by the total, 156, and multiply that by our 10-volt source. Boom, 6.41 volts. Finally, for V2, we do the same thing for the 56-ohm resistor, and we get 3.59 volts. And hey, notice this, 6.41 plus 3.59 equals 10 volts, our source voltage. Just like Kirchhoff's voltage law says it should. Perfect. So we've nailed the fixed divider. But what about that amplifier knob we started with? For that, you need an adjustable voltage divider. And that is exactly where the potentiometer comes into play. This is a great way to see how the physical part connects to the drawing on a schematic. A potentiometer, or we usually just call it a pot, is a resistor with 3 terminals. Between the 2 outer terminals, 1 and 2, the resistance is fixed. But terminal 3 is connected to what's called a wiper, a little contact that moves. As you turn the knob, that wiper slides along the resistive material inside, essentially splitting that total resistance into 2 pieces. By doing that, you're changing the resistance ratio, which lets you smoothly adjust the output voltage from 0 all the way up to the full source voltage. Okay, so now we get the theory behind both fixed and variable dividers. Let's talk about where you're actually going to find them out in the wild. The beauty of this circuit is just how versatile it is. You're about to see this one simple idea become the backbone for tons of electronic systems. And here it is, the answer to our very first question. In an audio circuit, that volume knob is just a potentiometer working as a voltage divider. The audio signal itself is the input voltage. When you turn the knob, you move the wiper, and that changes what fraction of that signal voltage gets passed on to the amplifier. A lower voltage means, well, lower volume. It's simple, it's effective, and it's in millions and millions of devices. All right, let's step up the complexity just a little. We also find voltage dividers at the very heart of operational amplifiers, or op-amps. In this case, a voltage divider is used in a feedback loop. It takes a little piece of the output voltage and sends it back to the input. This trick is called negative feedback, and it lets us perfectly control the insanely high gain of the op-amp. You're going to study op-amps in a lot more detail later, but for now, just remember, it's the voltage divider that makes them behave.
The voltage divider is also the fundamental bridge between the physical world and the electrical one. Think about it. A lot of sensors, like thermistors that change resistance with temperature, or these cadmium sulfide cells that change resistance with light, they don't produce a voltage on their own. But if you put them in a voltage divider, any change in their resistance creates a proportional change in the output voltage. And that's something a microcontroller can actually read and understand.
And finally, for a transistor to work properly as an amplifier, it needs a very specific, very stable DC voltage at its terminals. We call this biasing. And what's the most common and stable way to do it? You guessed it, a voltage divider. It sets a rock-solid DC voltage at the base of the transistor, which gets it into the perfect state to amplify an incoming AC signal. Understanding this is absolutely crucial for your future electronics classes. All right, we've covered the theory. We've seen the applications. Now it's time for you to put on your engineering hat. Let's apply this knowledge to a real, practical design problem.
Here's the challenge. We want to design a light-activated switch, maybe something for a nightlight. We've got a 4.5-volt source. We're using one of those CDS cells, a photoresistor, and we know its resistance goes up to 90 kiloohms when it gets dark. We need our circuit to trigger something when the output voltage across that CDS cell climbs above 1.5 volts. So the big question is, what value of the other resistor R do we need to make this work?
So the absolute key here is to think in ratios. Let's walk through it. First, just look at the voltages. Our trigger voltage, 1.5 volts, is exactly 1/3 of our source voltage, 4.5 volts. Okay, since we know voltage divides in proportion to resistance, it must mean that the resistance of the CDS cell also has to be 1/3 of the total resistance at that trigger point. Well, we know the CDS resistance is 90 kiloohms in the dark, so the total resistance must be 3 times that amount. 90K times 3 gives us a total resistance, RT, of 270 kiloohms. From there, it's just simple subtraction. The total, 270K, minus the CDS resistance of 90K, gives us the value for R, 180 kiloohms. Done. Now, to really truly get this, you have to practice. I really want you to pause here and actually work through these problems. Being able to look at a circuit like this and quickly analyze or design it, that's a core engineering skill you'll be using constantly.
So, let's wrap this up. What are the big takeaways? We've learned the voltage divider is the fundamental circuit for creating smaller, specific voltages from a larger source. It's the simple idea behind things like volume knobs. It's the absolute backbone of countless sensor circuits, and it's totally critical for making transistors and op-amps work correctly.
I'm going to leave you with this one thought. Master this circuit. Seriously, it's not just 2 resistors in a row, it's a fundamental concept for controlling, converting, and sensing voltage. You will see it absolutely everywhere in your career, from the simplest little gadget to the most advanced electronic systems. It is truly one of the most elegant and useful tools you will ever have.